All right, so now we're going to be talking about linear systems of equations. So let me sort of define this for you. So a linear system is a finite set of linear equations in a set of variables, which I'm going to denote x sub 1 all the way up to x sub n. And those equations have this general form, a11x1 plus a12x2 all the way up to a1n xn is equal to some right-hand side b1. And then you have a21x1 plus a22x2 all the way up to a2n xn is b2. And then an1 x1 plus an2 x2 all the way up to ann xn is equal to bn. Okay, so it's a system of n equations with n unknowns. Okay, so n equations and n unknowns. So this is called a system of linear equations, right? So this is called a system of linear equations. And basically what you're looking for is that you're looking for a set of variables x1 to xn which satisfies all these n equations simultaneously. Okay, so a set of numbers x1 to xn, right, is called a solution. Right, if it satisfies every equation in the system. Okay, so you know, and you've probably seen examples of this in low dimensions. So for example, in 2 dimensions, right, you probably know that each of the equations defines for you some sort of line in general, right? And so in 2 dimensions, you each of the equations define a line. It's like, and then the intersection of those 2 lines gives you the solution of that system of 2 equations and 2 unknowns. So more generally speaking, what happens is that if you're in this n-dimensional space and you have one of these equations, that each of those equations specifies a n-1 dimensional hyperplane. Okay, and when you intersect all of those n-1 dimensional hyperplanes, then you get in general, you get a unique point, right? So obviously, you probably know that it's not always the case that when you have 2 straight lines, it's like that there's an intersection. It could very well be that the lines are parallel, for example, or if they are, or they could be really right on top of each other, right? So there could be a situation where there isn't a unique solution, or that there's no solution at all. Okay, but generically speaking, if you take n equations in n unknowns, then generically there will be a unique intersection. And what I mean by generically is that if you were to sort of jiggle the coefficients a little bit, then what will happen is that there will be generally a solution of that system. Okay, anyway, so let's try to think about expressing this now using matrix notation. Okay, so let me just erase this bottom part and then I'll leave this set of equations up for now, just so that it's easier to see how we transcribe this system of equations into sort of matrix notation. Okay. So you've probably seen it before, but let me just remind you of this. Okay, so we want to write this system of n linear equations in this sort of matrix vector representation, Ax equals to b, where x and b are column vectors and A is some sort of square matrix. Okay, so so A is going to be an n by n matrix of the form A11, A12, all the way up to A1n, A21, A22, A2n, and all the way up to AN1, AN2, ANN. Okay, all right, so that's A, it's an n by n matrix, sometimes referred to as the coefficient matrix. Okay, and all right, so you have A like this, you can have x as a column vector, x1 to xn, and b, so this is the vector of unknowns, so it's a column vector. So this is the vector of unknowns. And then you have the b vector, which is b1 to bn. And this is just the sort of the right-hand side vector, if you will. Okay. All right, and then it's easy to convince yourself that if you, with this matrix and these vectors, you know, it's like the equation Ax is equal to b just reduces, it's like always equivalent to this set of n linear equations. Okay. All right. So now let me give you a definition, an additional definition. So if you look at a special case of this linear system where b is the 0 vector, so if you look at Ax is equal to 0, this is what's called a homogeneous equation. And then its solution of the homogeneous equation is called the homogeneous solution. So x that satisfies Ax equals to 0 is called the homogeneous solution. Okay. All right. So let me state a few theorems now about the solvability of linear equations, systems of linear equations. So let n be a positive integer. And let A be a n by n coefficient matrix. Then with those two sort of things, it's like then the following statements are equivalent. All right. So the first statement is that for each b, this right-hand side vector, right, ax equals to b has exactly one solution. So I'm basically trying to characterize under what circumstances this linear system has a unique solution and has a solution, right, in terms of other equivalent statements, basically. So for each b, right, ax equals to b has at least one solution. Okay, you might think these look quite similar. Yeah, I mean, it's anyway, so all right. And anyway, so these two conditions are equivalent to the following. So the homogeneous equation ax equals to 0, right, has only the trivial solution. Okay, so more or less it's like what this is saying is the following, that if you look at just the homogeneous equation, ax is equal to 0, and it turns out there's only one solution, and that solution is when x is equal to 0, then it turns out that if you now change the right-hand side to b, okay, that the equation, the linear equation ax is equal to b, will always have a solution, okay, so it has at least one solution, and that solution is going to be unique, okay. All right. So you might have encountered situations where it's like for specific a's there is a solution for a specific value of b, but not in general, right? So this doesn't actually fall into this situation, because this statement, the second statement in particular, is saying that for any possible b, you always have at least one solution, right? So the situations where you sometimes have solutions or not have solutions, or have multiple solutions, that sort of is usually, well, that's always the case, that it depends on the value of b. And in particular, what has to happen is that b has to be essentially in the image of this matrix A viewed as a linear transformation, right? So if b is in that image, then you can solve, it's like a linear equation like this, even if you have a situation where, for example, the homogeneous equation doesn't have only the trivial solution, but yeah, but again, that's not true for all possible b's in that situation. All right. So anyway. Okay, and again, if you've done some linear algebra, which you should have, it's like for the purposes of this class, then you know that these properties are related to this question of whether or not this matrix A is invertible or has full rank and things along those lines. So let me sort of just state that now. So the n by n matrix A is said to be invertible if for every b, a linear system ax is equal to b, right, has exactly one solution. Right. Otherwise, we say that A is singular. Okay. All right. So let's look at a bunch of possibilities, just using our two-dimensional example as illustration. Okay. So the remark is as follows, that for a given A and B, right, there are basically three solutions. Three possibilities. Okay, so the possibilities are that there are no solutions. Right, so A is singular. So the other possibility is there are infinitely many solutions. So again, A is singular here. And the third possibility is that there's exactly one solution, which means that A is invertible. So geometrically, what these correspond to are the following cases. So when there are no solutions, if you're thinking of them as straight lines, it's like you basically have straight lines which are parallel to each other. And if you think about what that means in the context of the matrix A, the 2 by 2 matrix corresponding to these two linear equations in just two variables, that more or less says that it's like the first row is a non-trivial multiple of the second row. Okay, yeah, so that's one situation. And then the other possibility is that you have you have infinitely many solutions, and that's what happens when L1 and L2 are right on top of each other, and that's when sort of this augmented matrix. So if you think of this A matrix and you augment it with this column vector B, the rows of this again are multiples of each other. Okay. All right. Whereas in this case, the rows of A's are multiples of each other, but the rows of A augmented with B is not a multiple of each other. Okay, so that will end up in a situation it's like where you have parallel lines, but they're not necessarily on top of each other. Well, they're not on top of each other, right? So this is case 1, right, which is no solutions. This is case 2, where there's infinitely many solutions. And then this is sort of the generic case, which is case 3, where there's just one unique solution. So, okay. So these the lines are parallel. Right, so there's no solution. And the lines coincide here. So infinitely many solutions. And then the third case is that there's one solution. Okay. So again, if you've done any linear algebra before, it's like you probably know that this is related to the question of whether or not the sort of all the columns, all the rows of the matrix A are linearly independent of each other. Okay, so let me just state this definition of linear independence just to remind you, and then what the implications of that are as it pertains to the question of A being invertible. Okay. So this is linear independence. So if you have z1 to zn, which are just a collection of vectors, then the vector y is said to be linearly independent of z1 to zn if you can't write y as a linear combination of the z1s to zn. For all possible values of c1 to cn. Okay. All right. Another way to sort of think about this is that you look at these vectors z1 to zn, and you look at the h-dimensional hyperplane which is spanned by it. Y is not in that h-dimensional hyperplane. Okay. You can also sometimes have some notion of linear independence of the set z1 to zn. All right, and again, it's like if the vectors z1 to zn are linearly independent, then the space they generate, the hyperspace they generate, the hyperplane they generate will be of dimension n. Okay. Anyway, there are many ways to sort of see this. Okay, so let me sort of state a theorem. So the n by n matrix A is invertible right if and only if all the columns of A are linearly independent and all the rows are linearly independent. So when we talked about the dimension of the hyperplane spanned by these n vectors, you might again, looking back on your class in linear algebra, you might know that that's related to this notion of rank, right? So so this condition here about linear independence can also be reframed. It's like into the statement that this matrix A has full rank, right? Okay. So, all right. So anyway, so that's sort of just a brief overview. It's like of the relevant concepts from linear algebra. It's like for the purposes of what we're going to do next. And what we're going to do next is to talk about numerical algorithms for solving systems of linear equations. And in particular, it's like we're going to primarily focus on the question of what happens if this linear system is very large. There are a lot of unknowns and there are a lot of equations. So how do you go about doing this efficiently, robustly on a computer, again, when you have a very large system of these linear equations. So let me just stop here for now.